So I'm quite happy that you guys are asking very good questions about assignment 2. It's good. So please work on your own a little bit and then work with your mates, okay, when you get stuck. Because some of you have some information about what was covered and others don't. So I just want to make sure that my screen capture is correctly working on YouTube. So the sound's okay. Right, so let's continue. So this is our main idea, right? So we want to start playing with this likelihood Bernoulli function. Oh, sorry, yeah. Likelihood for the Bernoulli. And we want to pass in larger sample sizes from our secret Bernoulli theta sampler, right? So we still don't know what theta is. And if you looked at it, don't tell anyone else, okay? And then we're going to just use a range to pick a bunch of values in 0, 1 and plot it, okay? So let's see. So you see, so we already saw n is 2. Can someone say what the underlying data is for this likelihood function with sample size 2, Bernoulli? Come on, guys. This is what? Theta multiplied by 1 minus theta, right? So this sample is 1, 0 or 0, 1. You with me? Okay, good. And that's a lot of time we spent on okay, so now we're going to make this, whoa, you see? So we make this bigger. Sample size gets increasing, 37. You see it's concentrating, right? Can you kind of guess when I have 37 samples from this secret theta star I drew my sample from, right? It's concentrating. It seems like it's concentrating around 0.3. You guys agree? So let's increase it, right? It's really peaking around 0.3 with 396 samples, right? Okay, so you see the point is, now look at the scale where, this probability scale of 3 times 10 to the minus 200. Okay, now do you understand why we want to do multi-precision floating point real arithmetic? Right, because these are little bugs. If you directly implement and float, you need to do quite a lot of fielding, numerics fielding. So there we go. So looks like the likelihood function is peaking and the argmax value is somewhere close to 0.3, right? So, yeah.
Why isn't it like smooth?
Oh, why is it like that?
Yeah.
Yeah, so,
The program.
It's, it's concentrating, right? Remember when we did the first plot? I said this is not really a plot. It's actually a bunch of dots. It's a polyline interpolation. So if you want it to be smooth, we can do some hard work. We can make the A range to go like that. Okay? So then let's try it. Are you happier?
Yeah.
Oh, it's good. That's a very good question. So, when I first learned about plotting, I didn't know this. I was much, I don't know, probably 11th standard in India or something. And I would always freak out. Sometimes the plots will come and I'm like, oh, is the definition changing? So anyway. Okay. The log likelihood function. This is the next most important idea. Why should I turn off this light? Is it too bright? Oh. Okay. So the next core idea is the log likelihood function. So this was our likelihood capital L, right? Just the product of the densities, joint density. But then we just take little l sub n to not be nothing but the logarithm of capital L. So we take log of the likelihood function. It's called the log likelihood function. Okay? And, well, you know all about laws of logarithms, right? Log of a times b is log a plus log b. So this product will become a sum when we do logarithms. Sums are way easier to work with, okay? That's one of the main punchlines. So this is just recall of logs, you know, log of A times B, log A plus log B. So in Sage, the default base is the natural, is the E. So natural logarithm. So if you want to change the base, you have to put another, another parameter. So log A base 10 is like that. Okay, so you know all about this. The log of products is the sum of logs. So this is what we will use heavily when we do calculations and computations for maximum likelihood estimators. Okay. So now, if the data is ID according to some probability density function, say for mass function, then the log likelihood little n of theta is the sum of the logarithms of the independent of each of the mass or density functions. Okay, and for Bernoulli, it works out like this. You see, ln of theta is log of ln, capital Ln, which was the theta to the tn, 1 minus theta to the n minus tn. So just by laws of logarithm, it's tn log theta plus n minus tn log 1 minus theta. Okay? So, yeah, anyway, I just put all of this so that it's like, you guys know a lot more calculus, so you don't need to know. So, you know, some of the things are maybe too much information, you know, so I can skip it. So this is just a little you try in class to you know, you should be able to derive this. This is not very hard. You should be able to do that in your head. So we're just using some laws of logarithms quickly to bring them down from powers. Okay. So let's do an interactive now. So now let's look at the same likelihood function on the left for some sample size and the log likelihood function on the right. Okay. So let's sort of increase the sample size, and you know, it's hard to see now, right? But look, the logarithm is now in negative 100 units, right? This guy is like 8 times 10 to the minus 34, right? This is some probability space, right? Products of probabilities between 0 and 1 will get smaller and smaller. When we move to the log scale. So the crucial point is this. This is peaking around 0.3, and so is this. Because logarithm is a monotonic function, which means if x is, so if x is less than y, then f of x will also be less than f of y, right? So it preserves the order in the domain when you apply a monotonic function to two numbers. The image is also preserved, the order is preserved. So although it's kind of hard to see that the highest point is 0.3 because it messes with our eye, we have to zoom in here, but that's what's going on, okay? So with that insight, let's get into maximum likelihood estimation in more detail. So estimating a parameter with the value that maximizes the likelihood function is essentially maximum likelihood estimator. And because it's a monotone function, for us, the argmax is preserved. That's all I'm saying here. So maybe I should put a box here for. So what's your name?
Hi.
Yeah?
Sarah.
Sarah. I think Sarah is right? This is like way too much information. So I mean, I don't want to, but if I put box and I don't put box somewhere, don't shoot me, okay? It's just okay. I mean, I'm not trying to, I'm not going to say everything that's important has a box around it, right? But so that's important, right? So we saw this before. Now this is the point, right? So because of the monotone property, theta and hat can just be argmax of the log likelihood itself, right? So that's, I mean, you know, you guys can take these notes. There are Creative Commons license. the source where I'm generating this from is actually unlicensed. So you can put your own name and whatever. So the idea is that you can, use this content if you want for your own notes. And okay. So that's basically the summary here on the board. So this is also equal to argmax, exactly the same, except now instead of capital, we have little ln, because that's the log likelihood function. So this will be on a different scale, but the point is little ln of theta will find the same point as its maximum as well. Okay. So what is the method, right? This is a standard type of question in the previous instances of this course. And we will see similar types of questions here as well, but in our sort of sage math world. So what do? You have to maximize a function, right? So if a function is just in one dimension, say theta is only one dimensional, how do you maximize a function if it's, say, differentiable or twice differentiable? Oh, that's awesome. Who said that? Good. Yeah, what's the idea? Say in 1D. So you can look at the derivative, right? The slope. And at the maximum, or say the minimum, say the function is like this. At the maximum minimum, the slopes will be 0, right? Yeah. So we can set the derivative equal to 0 formally, find the solutions for that equation, right? So find all the thetas where the log likelihood function is actually, the derivative of the log likelihood function with respect to theta is actually 0. And then we go to these solutions, and then what we can do is evaluate the second derivative of the log likelihood function, right, with respect to theta, and check that it is actually negative, right? Right? So how do I remember this? Because I've always forget this, but I have a very simple trick. So just think about, so this is x squared, and then flip it, right? So that's minus x squared. So we know 0 is where it's maximum, right? So the derivative of this is minus 2x. The second derivative of this is minus 2, right? So, I mean, but you can also mechanically do this, right? The rate of change should be negative at the maximum and stuff. So that's what we're, at least we're sort of setting this up here and trying to show you the steps. So d by d theta of little ln of theta, log likelihood equals 0. And then we solve for theta, right? So we just put in our expressions and keep going. And then we get theta and hat is Tn over n. So this is too easy. So you can, yeah, that's the main step, right? So then the question is, Tn over n is just the sample mean in this case, right? So it also makes intuitive sense. The probability of seeing heads is just the fraction of heads in the sample. This is too simple of an example. I have plans to give you guys a bit more fun stuff involving ODEs, so let's see. It won't be on the exam, but just to show you that same exact maximum likelihood estimator works in the most complicated ODE problems as well, if you have data for the problems. It's coin toss, yeah, but no worries with ODE and PDE parameter estimations. If the noise is Gaussian, so if you have a normal noise, standard normal noise. Okay, so here's our little interact. So now we know the maximum likelihood estimator is just the sample mean. So here's what we're plotting. For this simulation with just 2 samples, it's guessing it to be half. But of course, if I increase it, you see how it's slowly converging to 0.3 and stabilizing around 0.3. So we say the maximum likelihood estimator is asymptotically consistent, right? Because as sample size increases, it's converging to the true theta 0.3, theta star, right? Which, so should we see theta star now? How many of you have clicked that already? Those guys are messing with regexes, the other thing, I'm really paranoid. I really don't know, like, if you guys could be like hardcore, like, viral cryptology hacker types. I don't know. I'm so paranoid. I'm running it on some of my personal machines or machines I adore. So I'm making sure that there is no way you can, as far as I know. But if somebody really does something dangerous, then, they probably deserve an A anyway. So. Okay, so what is the secret data? Yeah, if you're really good, they'll come and talk to me, right? So we'll have jobs, right? So here is Bernoulli F inverse, right? So this is what I'm hidden. So Bernoulli F inverse, that's what we saw. We have to simulate from it using that. Bernoulli sample secret theta is setting theta to be 0.3. That's all I've done. Because we wanted to have pedagogical value so we can simulate and learn. And then this sort of JavaScript thingy for iDisplay thing toggles. So it's not that's what gives me this click thing, right? Okay. Where are we? Okay. Okay, so now let's actually look at some real data, right? Maximum likelihood estimation, real data, but for Bernoulli trials. So this time we will look at the New Zealand Lotto data again. This data is frozen for some historical reasons, right? So this is someone named Jenny Harlow in New Zealand. So we were working on some version of this course for second-year students in New Zealand at one point. So this is, this is second-year Kiwi course. Anyway, so this is our New Zealand Lotto data. But this time, of course, this is a equiprobable de Moivre random variable, right? Oh, by the way, this could be a coming attraction. So remember I told you that so far we've always looked at de Moivre as this 1 over k random variable, right? So its parameters is k of these. So we usually just call this k, right? But this is a special case. And I already showed you when k is 3, this is usually called the equiprobable. Depending on who you talk to, it's called equiprobable case, or it's called the uniform discrete case. So this is uniform discrete distribution on k outcomes. So then, of course, there's a non-uniform version, right? We briefly mentioned this, and I said the parameter space here is the unit simplex, right? So when k is 3, it's all the points on this plate in this triangle that sum to 1, right? So right in the middle is 1/3, 1/3, 1/3. Okay? That's what we've been seeing. That's enough for now, but the point is this could be any point on the simplex, right? It could be, I don't know, it could be just 1, 0, 0, right? That's really boring. But it could be any point here. That's 3 numbers that are probabilities that sum to 1, or any number of numbers. So the parameter estimation in this problem is also possible, right? Why not? You can just say, well, I have a bunch of observations. Anything that falls on this axis, I'm going to call 1, I'm going to call this 2, and call this 3. So I'll have a sequence of 1, 2s, and 3s, or ABCs, whatever, right? So then I count, and then I have a likelihood function for the de Moivre, right? It's a little more involved, but it's not too hard, okay? So what is that? The probability that, say, this de Moivre random variable takes 1 is theta 1, right? That it takes I is theta I. If I is in 1 through k, we will probably revisit this, and 0 otherwise, right? It's just theta 1, theta 2, theta 3. So you can say the parameter space is theta 1, theta 2, and theta 3. And the random variable takes values 1, 2, 3 up to k. Okay? And you can write down the likelihood function for this. It's just multiplications, exponentiations, laws of logarithms. Okay? That's a good exercise. But let's just get into real data very quickly. So now all I'm going to do is ask whether the first ball that came out of New Zealand Lotto is odd or even, right? So I just do a list comprehension with mod 2. So the remainder is 0 or 1. If it's 1, it's odd. So then I have my odd balls. My odd balls. Yeah, here are my odd balls. That's a lot, okay? So yeah, there's 546 ones. So the list has many methods, right? So I can just use the dot count method and count all the ones is what I'm saying. So there's 546. Of course, you could also do sum, right? I mean, you can look at the docs for it. So because the others are zeros, sum will also work in this case. So that's how we get our T sub n. So we're just in the Bernoulli land, except we're now using real data, that's all. So this is a very important change now, right? We're not just going after some pseudo-random number, probably the Mersenne twister under the hood that we're manipulating using this F inverse Bernoulli to create our own samples, right? Well, okay, the likelihood function made sense. So now let's say I'm going to use this Bernoulli model to actually attack a real data, while being fully aware that I have a mathematical assumption that is the model and some real balls that are like spinning with air jets flying around, right? Have you seen these lotto machines? It's a very complicated engineering operation, right? I mean, it's very, very important to guarantee stuff. So that's like physical randomness, right? That's a physical de Moivre equiprobable sampler. So that's it. So now we're going to use PyLab, CumSum, cumulative sum, and use this to create a cumulative sum of Bernoulli ball 1 odds, right? What does CumSum do? It just does a running sum, right? Which means for any point on the list, I'm going to have the sum of all the ones before, right? Which means it's going to give me the running sum. And so the running sum is my T sub n, right? My statistic I need to put into the likelihood function for the Bernoulli. So I'm just going to put it in and see what is the what it does next. And you know, here is just a detail, right? This is the blessings and curses of sage math. You know, 0 is a sage rings integer, and what comes out of a NumPy CumSum thing is actually an integer 64. For this operation, these things won't matter, but you need to kind of be aware of the types that are going in and out of different libraries. Okay, so first I'm going to create my sample size as a list that starts at 1 and ends at 1114, because that's my sample size, right? Every week or whatever the lotto happened for several years. So now I have my sample size n defined as a list. And the next thing I'm going to do is do this relative frequencies of the Bernoulli ball 1 odd. So what I'm doing a list comprehension here, I'm saying a tuple, I'm creating a tuple, right? It starts here, look at the completing green point, it's here, right? It's a tuple. If you want, you can put a bit more space to make it more pretty. Okay, and then it has 2 elements, right? There's only 1 comma. So it's a 2 tuple. The first element is I, the second element is the integer of the CS Bernoulli ball 1 odd of I divided by the sample space of I, right? So I'm giving it the sample mean. Okay, why am I giving it the sample mean? What is the sample mean for the Bernoulli theta trials and Bernoulli theta trials? It's the maximum likelihood estimator, right? That's what we just derived, right? So think about this. What did we do? What was the punchline of all of this? So we said the maximum likelihood estimator is the sample mean, right? Because we solved for the log likelihood function, set it equal to 0, and then we realized at theta, when theta is the sample mean, Tn is the sum divided by n, we get the maximum in the log likelihood function. So I'm just going directly after the maximum likelihood estimator of the New Zealand Lotto balls as they come out every week by using all the information up to now. Oh, fall. Okay, you see? And then the question is, if the machine is the same and it's behaving like an equiprobable de Moivre sampler in reality, then I will accrue more and more information, and maybe I will get closer and closer to Bernoulli half, right? Because it's fair to assume that if there are 40 balls, right? Is that true? Yeah, 40 balls. 20 will be odd and 20 will be even. Yes. So that's half, right? So that's kind of the game we're trying to play. So now we're sort of taking all of this theory and flipping it on its head and saying, let's see if the New Zealand Lotto machine is maybe rigged, or no. We're not doing a hypothesis test yet. We could. But we're just looking at the maximum likelihood estimator. And that's what this is. You run this. And so here we go. This is, on the y-axis, we're showing the maximum likelihood estimator for each sample, right? And then as the samples increase, the number of oddballs increase, we're plotting the running mean. The running mean is the MLE of theta. And you can see it's stabilizing around half, right? With enough samples. It looks like a fair de Moivre equiprobable sampler of the 40 balls. And of course, you split into odd and even, it's Bernoulli half-half. It looks like that. So later on, we can do hypothesis tests that is it really half or not for the number of samples we have. That's evidence-based reasoning in sort of whatever, management, science, and all sorts of places. Okay. Yes, we have effectively plotted the maximum likelihood estimate. So this is very important, right? I'm saying now I have plotted the maximum likelihood estimate, little theta sub n hat, right? For each n, for each sample size, I have only one sample, right? This list that's increasing, right? Number of the oddballs. So it's, because that ball that's popping out is only one realization, right? So what I have is an estimate, right? And the conceptual sort of background is that if I repeated this whole experiment again and again, say this is all science fiction, but say for instance there's parallel universes and there are New Zealand Lotto machines in each of them and they all have their own de Moivre sampler. And of course, the physics, whatever, slightly different. So the balls that come out will be different, okay? Then I'm gonna have lots and lots of running means, right? And so the maximum likelihood estimator itself is a random object, right? It's a random variable. So if I have lots of running means, we did simulations like this before, and I sort of take a slice for a given n, say 200. I ask what is the distribution of the maximum likelihood estimate. That itself will have a shape, right? So that's what we're going in the next notebook and coming back to regression on. That's justified by central limit theorem. It has some Gaussian, normal distribution, and so on. And that's what we need to really understand hypothesis testing. That's why we need to do that. Okay, what else? How are you guys doing? Some of you are like, oh my God. Oh well. I'm sorry, guys. I can't help it. I mean, there's a lot of stuff to cover, right? But it's all conceptual, right? You don't have to know how this interact works if you don't want to. Okay, so what I'm doing now is just plotting the log likelihood function based on 351 samples of this Bernoulli ball 1 odd, right? So we really control it and look at it now, the whole function, right? For that sample size, you look at the shape of the function, log likelihood function. So yeah, so it looks like it's sort of zooming in on half. Okay, and we're doing the same one here, except what we are doing now is introducing theta as a variable. So this is sort of the next main concept. We're going to get into symbolic calculations in Sage, where we define symbolic variables, and then we can do symbolic calculus on it. So here theta is bar, variable string theta. So then n is 1, and t sub n is C as Bernoulli, ball 1, odd, n minus 1. So that is the last the full sample, right? All of them. And then I'm just plotting now the symbolic variable Tn times log theta plus n minus Tn times log 1 minus theta. So and then what I'm actually just showing you this plot symbolically. So this is because what we are doing here is exploiting the fact that we have an analytic expression that is that can be expressed symbolically, because logarithm, multiplication, addition, subtraction, as long as we introduce theta as a variable, is fair game now. So we have all of symbolic math packages in Sage at our disposal. Okay, so let's get into that next. And yeah, so this is basically the same idea. But we're looking at larger values of n. We can see the shape of the log likelihood function settling down as n increases. And the color has been used to show changing values of n, which results in each curved line on the plot and so on. So as we increase n, it's going from blue to red. So, and of course, you know, it's the log likelihood values are going down. Right? So this is, you see, because the likelihood is getting smaller and smaller because you're multiplying probabilities. So the log likelihood will go lower and lower. But it's going to get curved more and more. It's going to get concentrated at half. It's kind of... All right. Using Sage for basic algebra and calculus. So what do you guys do for basic algebra and calculus right here? How do you use the machine? Use Maple or... You guys are, okay. Yeah, anyway, I don't know. It's so yeah, this is kind of the main reason we got into Sage, right? This is a huge universe in Sage Math you can use for a lot of problems. So let's just quickly show you the ropes. So when I say x is 1, type x, you guys know this is just our Sage rings integer, right? So now when I say x is var x, so this is symbolic expression. That's how we did the visualizations above, right? So what is this? Type of x is Sage symbolic expression. So you can overload on it. So you can look at the docs for this, doc string for this. It's create a symbolic variable with name s. It has, you can do multiple variables quickly. There are various keyword arguments. Yeah, so here's 3 symbolic variables. What else can you do? So here's an expression, an algebraic expression out of them. F is the function. That's x to the n plus y to the n plus z to the n. And then f comes out as an expression. So you have this whole function, and you can do, you know, you can do calculus directly on it and algebra directly on it, and other things. So you can choose the domain where these variables live. You can do, you know, you can specify constraints on the real parts, imaginary parts, or whatever, you know. So you guys know complex arithmetic, right? You've seen complex arithmetic. You've seen a lot of linear algebra. I'll kind of drop you a little bit into, say, just linear algebra, just enough when we do regression. But you can dive deep on your own. There's quite a lot there. Yeah, so let's just the short doc string. I think the double question mark is much bigger. So let's try a simple example, solving x squared plus 3x plus 2 equals 0. Why are we doing this? Because you want to solve the maximum likelihood equation, you know, by finding the derivative of the log likelihood on the left. So this is all you do. Solve x squared plus 3x plus 2, comma x. So this comma x is solve it in terms of x. Set this equal to 0 and solve it in terms of x. So x is -2 and -1. This is a quadratic. So we can use solve if we have variables instead of known values for the coefficient. So for example, let's say you have x, a, b, and c. Declare all of them as variables. And now you do solve a times x squared plus b times x plus c equals 0. It can be explicit. And say I want to solve it explicitly in terms of x. Cha-ching, right? So then you're just getting what is this? You guys know this, right? You've seen the geometric construction in high school. The solution to the quadratic, right? Yeah. Yeah, so yeah, square root of b squared minus 4ac over 2a. I went to school, high school in India when I was much younger, like in the 80s. It was kind of, I think it was legal to be punished, or in school. I went to like a military monastery school, so we had to wake up at 4 in the morning and heat the water for the little kids. I was only in 6th grade, I was up myself a little. Anyway, it was an interesting school. I liked it. So anyway, I had to memorize it, and I refused to memorize it if I don't understand it. So I had like a lot of spanks for a while. No. So anyway, this is it okay for me to blabber random things like where I lived and stuff? Because that's totally okay in New York, So, all right. So here is where we're trying to solve a system of equations of several variables, right? So x, y is var x, y, x plus y is 6, x minus y is 4. Give me the solution in terms of x and y. So these are, again, very nice things. So you can see this as like rows of a matrix, right? And you're solving the system of equations. There are more formal ways of doing this, but you can start seeing it like that. So sometimes Sage cannot find an exact solution to the equation. So this is important to bear in mind. So you will get something like this back. You're saying solve cosine of theta is sine of theta, theta. It says sine of theta is cosine of theta. So it's not like you need to know what you're doing as well. You can use find root. This is very powerful. Find root cosine of theta is sine theta. In the interval, so this is the search interval 0, pi over 2. So that's where these two functions meet. Right, you can get into the doc string, about root finding, and this is important, right? Now we're getting into stuff we will use in maybe assignments or exam in the class. So I say u is a variable, okay? And this is important point, right? You're saying u is the variable of the string u, right? So it's something you have to do first. Now I'm asking you to differentiate sine of u in terms of u. Okay, so if you have a very complicated log likelihood function you would work out from the problem, then once you've done that, you can just pass it to the diff function. It'll give you, if it can, the derivative in terms of u right away. Well, sine of u is cosine of u, right? So it's adjacent side and opposite side on the circle. So we can also tackle higher derivatives, such as the fourth derivative of sine x squared in the following way. Sine x squared of the fourth derivative, right? So you don't want to sit there and do d by dx, and you can. But if you can do it by hand, and you understand things well, then it's totally okay to do it by computer, because you can focus on other aspects of the problem. So this is what it is. And then you can get into the doc strings, as always, to find out more syntax. Partial derivatives can also be found, right? So now you can use this to check your answers in other calculus courses as well. I believe the department is planning to introduce Sage Math in a year or two to all the new students who will be coming in. Yeah. So partial derivatives, so you basically have two variables, x and y, and then f is x squared plus 17y squared, and then you now differentiate f with respect to x, and you can, differentiate it, the function f with respect to y. The integral function is very useful. course. So it gives you the symbolic integral, right? The antiderivative, whatever you call it. So it's x times sine x squared is an example, and I want to, here's the integral for it. So let's quickly visit symbolic expressions in the next 3 minutes for maximum likelihood estimator. What do we do? Let's go back to our simple example, Bernoulli log theta. This one's simple, but why not? So we first do theta and Tn to be variables. This is very important, right? If you're going to work in symbolically, you have to introduce some symbolic variables, bar. So then log L is Tn. So now you have an expression for the log likelihood, right? With all these symbolic variables and existing functions and arithmetic operations. Then d log L is log L dot diff. So now you have the derivative, right? Called as d log likelihood. So it's n minus theta over theta minus 1 plus Tn over theta. Is that clear? Okay. So then solve d log L equal 0. Solve this expression to equal 0 in terms of theta, right? We just did this by hand before. I mean, by whatever. So now you have the answer. So it says that there is a solution. There's only one solution, and it's at theta equals Tn over n. That's our sample mean. So you can play around. This is good. It'll pay off in your other math courses. So here's the philosophy in 30 seconds, right? What is the principle here? This is called the maximum likelihood principle. Suppose you have 3 coins, right? I go to some strange concert, like whatever. And then there's somebody saying, oh, I have 3 coins. If you can guess, I'll give you a cookie or whatever. And she swears that 3 coins are different, right? One has bias quarter, the other one has bias 3/4, and one of them is fair. And the game is, I'm allowed to pick a coin and then flip it so many times, n times, and then I have to guess what the true bias is, right, of the 3. Just 3. What we did before is we allowed theta to be any real number in 0, 1, right? Now just think about it. If it's just 3 and I flip it, and she's really telling the truth, she's called the oracle in mathematical statistics, right, this entity. And that's how you do a lot of justification of machine learning algorithms formally, right? Because if I go to an airport and then the iris scanner reads my eye and say, oh, you're not Raazesh Sainudiin, then I want to be able to question by law what the Vapnik-Chermaninkas complexity of that particular algorithm is when it tells me, right, that I'm not who I am. And as I'm not a European citizen, but you guys have a right to an explanation, you know. But I'm a human being, I have a right to an explanation as well. So these are extremely important notions, right? So there are these things called oracle inequalities that are at the heart of like statistical machine learning and so on. And they actually just have these simple ideas taken much further and further up. So yeah, the idea is simple, guess what it is, and you can just read this slowly. So if I have heads, tail over 3, you know, I get a likelihood value if I get a different sequence. So you can ask, if the coin is this versus that versus this, these 3 biases, what is the likelihood? And if you work it out, intuitively it'll make sense to you why the likelihood principle kind of works, right? Because, you know, if the oracle isn't lying and these are the true biases, you're not even evaluating a function over all theta, right? You're just evaluating the data that you're getting to test which of the 3 it is. So that's called the maximum likelihood principle. That's kind of the philosophy behind it. All right, I will see you tomorrow. We'll continue with maximum likelihood estimators for the exponential random variable.